Hello viewers, welcome back. Emoste from Agbe here. You can subscribe to my YouTube channel Emoste Online Class. Follow me on TikTok, Emoste Online Class, and of course on Facebook, Emoste Online Class and Emoste Kumagbe. We have a problem here on the board, and the question is we should calculate the current that must be passed into a solution of aluminum salt for 1 hour 30 minutes in order to deposit 1.5 gram of aluminum. If you take aluminum to be 27. Now, this is quite a very simple question. This question is very simple, but students need to pay close attention because there are some tricks, there are some things we need to do to get the final answer. Now, let's get a solution right away. Now, from the question, the time given is 1 hour 30 minutes. The time given is 1 hour 30 minutes. So first we need to convert 1 hour 30 minutes to seconds. And how do we do that? We need to convert 1 hour 30 minutes to seconds. And how do we do that? First, note that 1 hour is equal to 60 seconds. 1 hour, sorry, I beg your pardon, 1 hour is equal to 60 minutes. 1 hour is equal to 60 minutes. So So 60 minutes plus 30 minutes, you have 90 minutes. So 90 minutes, we have converted 90 minutes to seconds and we have 5,400 seconds. So that is it for time. Now the next thing is mass to be deposited is 1.5 gram. Mass to be deposited is equal to 1.5 gram. Mass to be deposited is equal to 1.5 gram. We don't have the value for quantity of electricity. Q is unknown, and of course the major problem is we should find the current that must be passed. So we're looking for Q and we're looking for I. Q is the quantity of electricity and we're looking for I, which is the current. Now this is the major problem. So we should find the quantity of electricity. So we should find the current that must be passed. So that we need to find Q first. So how do we do that? Now let's begin the solution right away. We need to write the half-cell reaction for this kind of question. Now for aluminium, which is a trivalent element, the half-cell reaction will be as follows. So this is the half-cell reaction for this question. Now that means 3 Faraday will be required to liberate 1 mole of electron in this kind of question because this is a trivalent element. So 3 Faraday will be required to liberate 27 grams of aluminium, and 1 Faraday is equal to 96,500 coulombs. So 3 Faraday will be equal to 3 times 96,500 coulombs. So 3 times 96,500 coulombs will give us 289,500 coulombs. Therefore, 289,500 coulombs will be required to liberate 27 grams of aluminium. Now, what we're looking for Q, what then is the quantity of electricity that will be required to liberate about 1.5 grams of aluminium. So how do we find our Q? By cross multiplication. So once we cross multiply, we're going to have Q times 27 being equal to 289,500 coulomb times 1.5. So our Q will be equal to so if you check our calculator, we're going to have 16,083.3 coulombs. Our quantity of electricity is equal to 16,083.3 coulomb, and that is Q. Now, but that is not the final answer, because the question says we should calculate the current that must be passed into a solution. So we're finding the current and not quantity of electricity. Now, how do we do that? We're finding the current and not the quantity of electricity. Now, in our previous videos, I had established that Q is equal to I times T, that is current in ampere times time in seconds. So this is what we're looking for. We already have our value from the calculation. We have the value for Q to be 16,083.3 coulombs. We're finding I, which is the current. We have the value for time, which is 5,400 seconds. So we want to make I the subject of the formula. And how do we do that? Our I will be equal, that is current, will be equal to quantity of electricity divided by the time, that is I is equal to Q over T. Now our Q from our solving is 16,083.3 coulomb. And our time from our conversion is 5,400 seconds. So if we check this out, we're going to have 2.98 ampere. And that is our final answer. Therefore, 2.98 ampere will be required to deposit 1.5 gram of aluminium, and that is our final answer, 2.98 gram.